Guys, today I'll be talking about rotational kinematics, aka the physics of a wrecking ball. And swinging from a chandelier. Okay, so anyway, for this video, I'm going to assume you already know the topics of normal kinematics, dynamics, and work energy and power. In fact, I have this chart here, which I'll use to help you to draw parallels between normal kinematics and rotational kinematics. But before I actually start on rotational kinematics, you need to know about radians. So first, let's assume you have a circle. Okay, 大概. Okay, something like that. Radius R. Yeah, so this is R. So right, um, so circle has 360 degrees in the middle. What's the circumference? Circumference. So 360 degrees. The circumference of the circle is 2 pi r, right? I times the diameter, which is 2 pi r. Let's say instead you have a semicircle. It's 180 degrees in the middle, right? So say you want to find this outer length, the, the this outer length. So it's half a so it's half the circumference of a circle, right? So assume the radius of this is also r. Its outer length is pi r. Okay, so now let's say you have a sector that is 9 has 90 degrees inside. The 90 degrees. The radius is still r. So the length that this angle subtends. Is it? Okay, so yeah. So anyway, this outer length is like, for 90 degrees. Length is pi r over 2. Let's divide this thing by 2. And what if you have 60 degrees? This sector is 60 degrees. The radius is still r. So 60 degrees, the outer length is this thing divided by 3. You can see, right? Pi r over 3. Okay, so so if you have a sector that's 360 degrees, you have 2 pi r. The circumference, the outer length is 2 pi r. 180 degrees, the outer length is pi r. 90 degrees, the outer length is pi r over 2. And for 60 degrees, it's pi r over 3. So what if what if would it what if you can represent what if you can represent, you can use these values to represent the angles instead of instead of 160 degrees, like all these degree values. Let me explain. Alright, 2 pi radians, I'm talking about radians now. So 2 pi radians corresponds to 360 degrees. Pi radians corresponds to 180 degrees. Pi over 2 radians corresponds to 90 degrees. And pi over 3 radians corresponds to 60 degrees. You can probably tell by now. Okay. So basically, instead of saying a circle has 300 has a 360-degree angle, you can say it has an angle of like 2 pi radians. So what's the advantage of using radians? So let's say you have a sector of, I think I'll draw it here. Say you have a sector of, okay, so let's say you have a sector of 59 degrees and the radius is r. You asked to find this length. This length. So if you know if the angle is represented as 69 degrees, then to find this length, you're going to have to do is going to be a bit complicated because so first you know the first if it so let's say this thing is a circle, it's 2 pi r, right? The circumference is 2 pi r. So this length is 2 pi r 2 pi r times 69 over 180 degree symbol, which is uh which is 23 over 60 pi r. Okay. What if this angle is represented in radians instead? This angle, when converted it to radians, is um, let's see, pi r. So this angle, when converted to radians, is basically just um, 23 over 60 pi radians. Okay. So the advantage of using radians is that, let's say if you want to find this length, all you need to do is multiply the value of the angle, the radius, and you can get this outer length. So as you can see, 3 over 60 pi radians corresponds to the value in front of here for the outer length of this sector. Okay. And fun fact, right? One one radian. Okay. Let's say this is 1 radian. let's say this is 1 radian. So 1 radian corresponds to about 57.3 degrees. And in rotational kinematics, right, all the angles are expressed in radians, so that when you do conversions to length from angles to lengths and vice versa and stuff, it is easier. Okay. Okay, right. So now that we've talked about radians, let's move on to the actual rotational kinematics. So first, let's refresh our memory on normal kinematics. So so you've learned about displacement, velocity, acceleration before, right? Yeah. Like so let's briefly talk about them again. So this, say you have a car. Yeah. Let's say you have a car traveling on a road. Yeah. Then displacement is the vector form of distance. So basically, yeah, if car the car has traveled 5 meters 5 meters in one direction, then the displacement is 5 or -5. And if the car reverses, then the displacement will reduce. Then velocity is the vector form of speed. So if its car is traveling at the speed of, you know 10 km, let's say 10 km per hour in this direction, then um yeah, its velocity is 10 km per hour. But yeah, if it reduces, um, 10 km, but then if it's reversing at 10 km per hour, then the velocity is negative 10 km per hour. Then for acceleration is like speed going up or going down. If this increases by 1 km per hour, um, for each 1 km per hour, then the acceleration is like just positive 1 km per hour square. If it but if it goes down if it goes reduces by 1 km per hour for each hour, then it's negative 1 km per hour square. So this all these can be applied to angles as well in rotational kinematics. So let's say, um, like if a string, if a ball at the end of the string, and string is rotating around a point here. So it's, yeah, basically this ball is spinning around. Basically you have this ball going around and around and around. Yeah. Okay. So so displacement, velocity, and acceleration can also be applied to angles as well. So let's say uh let's say um some time ago, this string and ball thingy was actually here some t- some time ago. So then the angle here is, let's say, 60 degrees, or pi over 3 radian. Wait, yeah, pi over 3. Then um the angular then the angular displacement is, yeah, pi over 3. So when it's applied, when displacement, velocity, and acceleration are applied to angles, they're called angular displacement, velocity, and acceleration. Yeah, so this is angular displacement. Let's say 1 second later, this ball will be mm, will be here, and the angle here is pi over 6. The angular velocity is pi over 6 radians per second. And for acceleration, angular acceleration, you should be able to tell by now. So let's say um, the angular acceleration is positive, I don't know, pi over um, pi over 12 radians per second. Radians per second square. Then here, like, okay, let's say from here to here the velocity is constant. Then the then the velocity here is over 6 radian per second. Then it and then sometime later um the velocity, I mean 1 second later, when the ball is like here or something, the the velocity will increase to over 4 radians per second. Okay? Yeah, so mm, so this is angular displacement, velocity, and um and acceleration. So and angular displacement, velocity, and acceleration aren't represented using the represented using S, V, and A. They are represented using Greek letters. So angular displacement is represented using Greek letter theta. Angular velocity is represented using the Greek letter omega, which kind of looks like a W, but it's curved down here. And angular acceleration is represented by the Greek letter alpha, which is kind of looks like an A. Okay. Hmm. Okay, so I've added these things here, and in fact, let's recall the four kinematics equation. V equals U plus AT V square equals U square plus 2A S equals half U plus V T, and S equals half U no UT plus half AT square. Okay, these in fact can be applied to rotational kinematics, to the angular quantities in rotational kinematics as well. So you convert S to theta, V to omega, and A to alpha. Yeah, wait, and there's in U also, right? So convert U and V to omega subscript I for initial, and omega subscript F for final. Omega initial, omega final. Okay, so you do these conversions, and you have omega final equals omega initial plus alpha t. Omega F square equals omega I square plus 2 alpha theta. Theta equals half omega I plus omega F t, and omega is also equal to WIT plus half alpha t square. Okay, so in fact these equations can be used in rotational kinematics if you ever need them. Okay, so I've added the equations, and as you can see, these things are red now. So in fact, angular displacement, velocity, and acceleration aren't the only quantities in rotational kinematics. So they're also tangential quantities. So what do I mean by that? So that's tangential acceleration. There's also tangential displacement, tangential velocity, and tangential acceleration. So let's use the string and ball example I used just now. Okay. Okay. Yeah. So yeah. So yeah. So let this be the circle be basically its path of rotation. Okay, quite bad. But anyway, let this be the circle, and so I've already talked about um I've already talked about angular displacement, velocity and acceleration, right? So okay, so first let me talk about I'll explain tangential displacement. So this be the circular path of the ball, and let this be r, the radius of the circle, and also the length of the string. So let's say um, the ball covered a certain distance here. The angular displacement is a certain quantity. What is this distance? This distance is the tangential displacement, and it's also represented by capital letter S, like normal displacement. What's the relationship between S and theta? Shouldn't be too hard to guess. Yeah, so S equals R theta. Don't forget, angles are in radians, so you can just multiply them by R to get this length. Okay, then for, yeah, so that's it for tangential displacement. So next is tangential velocity. So let's say 1 second later, one sec, let's say it's currently it's currently that this ball is traveling at a constant angular velocity. So this is 1 second later, this is omega, so this will be omega. And so what's the tangential velocity? The tangential velocity, okay, never mind about it. Yes, so basically, say now it has a tangent, an uh, angular velocity of omega. Okay, so what I'll draw here. What's the tangential velocity? It's basically a vector, yeah, a vector here that is representative of the velocity that is represented using small letter v, like normal velocity, and also v equals r omega. Okay, so this is tangential velocity. It's kind of like it's quite similar to tangential displacement. For one thing, the vector is straight. The vector is straight. It's not like it doesn't like curve along the path of the circle or whatever. Because like let's say this ball keeps swinging and hits a random wall here. The momentum v doesn't go this direction. It goes straight inwards. Okay? And lastly, tangential acceleration, which you should probably be able to tell what it is by now. So let's say other than the um, tangent angular velocity that the ball already has, there's an extra angular acceleration part. Then tangential acceleration is basically whatever effect this angular acceleration has on the velocity. So yeah. So basically, if for example the ball at this position starts going faster, yeah, starts going faster, then yeah, yeah. So it's due to the angular acceleration. Like it always affects this tangential velocity by magnitude of r. So acceleration is tangential acceleration is represented by a, and A is equal to R alpha. Shouldn't be too hard to understand. Okay. And this here. Okay. Okay, so I've added these in, and one thing I forgot to mention just now is that tangential acceleration, like, is as represented like as when represented as a vector, is like the velocity vector, tangential velocity vector. It's a straight line sticking out from the ball or whatever is rotating. Okay, so you may have noticed I've left a space here in the acceleration portion for rotational kinematics. It's because there's not just two different types of acceleration for rotational kinematics. There are three. What's the last type of acceleration? The answer is centripetal acceleration. So it's like, let's use the string and ball example just now again. The string, the ball. Um, the Here's the path of the ball, very badly drawn, and and actually, yeah, I should draw it better. Now it's better. So yeah, so here's a circular path, and let this be the velocity vector. I should start from the center of the ball. This be the velocity vector, tangential velocity vector. So okay, so here's a tangential velocity vector. You may be thinking, if this velocity vector is straight and there are no other forces or whatsoever acting on it, then why is this ball going in a curved path instead of going straight? Like, if there are no other forces whatsoever acting on the ball, then the ball would be going straight, like following this path, this straight path, instead of going in a circle. So what ensures that this ball stays in a circular path? In a circular path is something called centripetal force. Centripetal force is I'll use a different color. The centripetal force is acts in this direction. This direction. Okay. I'll use F subscript C to represent centripetal force. So centripetal force, right? So what's the relationship between centripetal force and centripetal acceleration? So you've learned F equals ma before, right? So yeah, the relationship is just Fc equals mac, where m is the mass of the ball. Yeah, so what is the magnitude of the centripetal acceleration? So yeah, so for that, right, let's do this. So let this be basically that this be some random dot. So yeah, I'm going to plot something. So basically, let this be like a compass for the, like some so-called compass for the velocity vector. Like basically, okay. So that first assume that this ball is going rotating with a constant velocity, both tangential and uh, angular. So let this be like um, the compass, like it basically reflects the direction of the velocity vector. So like if the velocity vector is pointing in this direction, then it will be like this, and so on. So when the ball, yeah, so when the ball is here, the velocity vector is pointing in this, is pointing like this. When the ball is here, the velocity vector points like this. And and yeah, the here this. And when the ball is here, for example, the velocity vector is pointing in this direction, and here, yeah. So it's kind of basically as the ball rotates, notice the velocity vector is also changing its position. Like you can like try imagining it going around like a clock or something, like slowly, like it rotates at the same speed or angular velocity as the this ball. It's like yeah. So basically, it's this is a centripetal acceleration of force, right? So yeah, so this is the centripetal acceleration. So it's kind of like this radius and the velocity vector, and compared to this and this is similar. Like it's almost like this vector is pulling this thing around the circle, like how the velocity vector is pulling the ball or the radius line. Like I don't know how else to explain this, but anyway, it's like the ratio, like basically like there. So from this, you can tell the ratios are the same, and so this is the ratio of this is v over v to r. So ratio of this to this is also v to r. So basically, AC equals v over r times v equals v square over r. Okay. We also know v equals r omega. So AC can also be represented as v omega or r omega square. Omega is the angular velocity. Okay. So yeah. So the for so the centripetal force and acceleration, they always act toward they always act towards the center of the axis of rotation, no matter whether this thing the velocity increases or decreases. So like it's like if you like let's say the ball is here, you freeze time, and somehow the velocity here is bigger than here, then the centripetal force won't point in a different direction like here or here. you always point towards here. It's just that the force required to keep the ball in orbit, so-called, um, is more. Like the force here is more than here. Okay, so that's centripetal acceleration. Okay, so I've added centripetal acceleration here. So now I'll talk a bit about mass. So mass, right? Yeah, mass is what it is. But in rotational kinematics, like, there has to be some form of mass to use that also takes into account the radius. Like like use the ball string example just now. So yeah, so the ball is on a string rotating around an axis of rotation. So right, the force. So like let's say the radius is 1 meter, then the force when you exert a force to cause this ball to rotate, compared to when this radius length of the string is 2 meters, force will not have the same amount of magnitude of force, won't have the same effect. Like like for 1 meters, if you want to exert a for 1 meters, if you exert a force and make this thing rotate, compared to when it's 2 meters and you exert the same force to make it rotate, they rotate at different speeds. Okay. Yeah, so there's be like some unit of mass that in rotational kinematics that takes into account the radius also. So I'll explain later. So let's talk about torque. Torque, if torque, let me spell it out for you first. Torque. Okay, make note of this word, torque. So if you go to Wikipedia and you search torque, you will find that it just says, what does it say? Basically, torque, moment or moment of force, is the tendency of a force to rotate an object around an axis, fulcrum, or pivot. Just as a force is a push or pull, a torque can be thought of as a twist to an object mathematically, blah 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 blah. So it's basically like how what 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 effect um what effect will a force have on an object when you apply it. Okay, so like said just now, with different radiuses, the force will affect the speed of this ball differently. Okay, but torque is basically like a function of force or something. Like it's not okay. So it's mm, not like F directly, but it's okay. So first torque is never mind. Torque first it is, I'll say, it's represented by the Greek letter tau, which looks like this kind of, and it's not equal to the force directly. Like it's equal to, like, this is equal to force times something or whatever, or even force square or whatever. Like, okay, it's not force itself. Yes, and basically the definition of torque is kind of like torque is directly proportional to the angular acceleration. Okay, and in fact, this is like it's the moment of force. So in a way, it's like F equals ma. So here is supposed to fulfill the equation I tau equals I A, I alpha, I alpha. Yeah, I is called, anyway, I is something called moment of inertia. It's like this is similar to, its relation to m is similar to um force relation to force. Like it's not force, it's like I is not mass itself, but is um like something about mass. So it's called moment of inertia. I stands for moment of inertia. Okay, and so tau is supposed to fill this equation, but what is it? Alright, it's bringing something called work done. So work done, you already know, it's, refresh your memory, it's equal to force times distance. But when you apply it in the rotational kinematic sense, like let's say, oh god, this is the circular path of the ball. Yeah, really decent this time. Yeah, so like, let's say you apply the force for a certain distance. Yeah, let's say for this distance or displacement, and this distance of displacement, okay, and this is the angular displacement. So this is equal to f r theta, f r, this is equal to f r theta, and so like, and it's basically because like torque is how, it's like torque is proportional to angular acceleration, like how mm, okay, so basically this is somehow so this is supposed to equal to this, and yeah, so torque equals, okay, so basically torque is equal to force times the radius. Like I don't really know, okay, so I don't really know how to explain it, but okay, so let me, okay, so let me give a demonstration instead. Okay, so say you have, okay, let me just give a demonstration. Let's say you have a man, let's say you have a man and his son, and they go to a playground. The playground has a seesaw. Hmm, here's a seesaw. So the man and son sit at opposite sides of the seesaw. And the man sits here. Sits here, which is, he sits 1 meter away from the center of the seesaw. So, and let's say the man is 70 kg and the son is 35 kg. So basically the man is twice as heavy as his son. So where should the son sit for the seesaw to be balanced? The answer is 2 meters. Okay. Oops. Okay, make it smaller. Yeah, so here's the sun. And if he sits 2 meters and doesn't do anything, like doesn't jump up and down or whatever, basically the seesaw will be balanced. Why is this the case? Because torque is force times radius, right? So you can see the torque is equal on both sides. On both sides, 70 like the force is the force here is twice of the force here, but the radius here is half of the radius here. So torque is equal on both sides. Because of that, like torque is directly proportional to angular acceleration. Like like when you balance out the torque and stuff, you get no net torque or no net angular acceleration. So the seesaw won't move down here or here. Okay, yeah. So so basically we have torque equals IA, and note this is torque is equal to FR, and I and alpha, alpha is equal to A over R, tangential acceleration. So I equals F R square over A. No F equals MA, right? So I equals MR square. So I is called the moment of inertia, and it's equal to MR square. Okay, I should really add something here. Okay. Okay, so I've added these things, and just now I didn't really explain clearly like moment of inertia, and torque and things like that. So basically, okay, I'll explain it better now. So it's like, let's say you apply a force. Say it's a spinning object. You apply a force and you make it spin faster or slower. You can use like F equals ma to easily find like how it will affect things, how it will affect the tangential acceleration easily, right? And basically use F equals ma to find that. If you want to find out like how it will affect the angular acceleration, if you're concerned about the angular quantities only, then it's better to use things like torque, torque, which is moment of force. It's better to use things like torque and moment of inertia. Like torque is torque equals moment of inertia times the angular acceleration. You can easily use that. Like you can use that to more easily find how affect the angular quantities only, if you're only concerned about that. So yeah. So that's kind of why I made torque red. Okay. And there's also something else called, like, there's momentum, and there's something called angular momentum. So basically it's angular momentum is kind of like, yeah. So actually wait. So if you know momentum momentum already. So momentum, linear momentum in normal kinematics is normal dynamics is represented as uh yeah. Actually, you know what? I can just do this. It's represented as T equals mv. Okay. Yeah, this is normally what it's supposed what it's like. But there's something called angular momentum. And basically, so angular momentum is represented as capital L, a capital L, and and like how torque is proportional to like how torque is proportional to alpha. Wait, actually, directly proportional to alpha. Angular momentum is directly proportional to omega. In fact, L angular momentum equals the moment of inertia times the angular acceleration. Also, right, so let me do a bit of math. Equals mr squared omega equals mr v equals r p. P is mv, the linear momentum. So it's like how torque equals force times radius. L angular momentum equals the linear momentum P times R. Okay. Okay. So I've added a few things. So yeah, so notice first I've added linear to the end of this tangential and here. So I've added angular momentum and these things. What's the difference between like this the red part and the green part? So let me explain. Like and also what's the difference between this and this and this. So okay, so like let me use the example of a wrecking ball. Yeah, wrecking ball. Here's a wrecking ball, and here's a wall. It's going to hit. Yeah. So hmm, okay, so here's the direction of the wrecking ball, right? Boom. So it impacts the wall here, and it has a bit. So the wrecking ball has a bit of has some linear momentum and some um, angular momentum, right? Yeah. So when it hits the wall, how much momentum goes through is only dependent on the linear momentum. So so it has a bit of momentum. It hits the wall, and this moment travels in this direction throughout the wall and breaks it. And yeah, but the angular, so this is the this is for rotational kinematics, like the m and the v, the tangential velocity, and it is actually no different from, like, say here. Okay, okay, like it's actually no different from here. You have a cannon. How to draw a cannon? Okay, I don't know how to draw a cannon, so just draw this. So it's no different from here. There's a cannon, and you fire ball, and you fire a ball, same mass and velocity at the wall. Like there's no difference from a wrecking ball you go and hit the wall, then firing this cannonball with the same mass and velocity to hit here. Like the momentum is the same in the same direction, and there's not much difference. And there's no difference on the perspective of the wall. Yeah, yeah. So this is mm, this is like from the linear perspective and from the angular perspective. Now, finally, let's talk about come on. Let's talk about work, work, energy, and power. Basically, how it applies in in rotational kinematics. So first, you recall the equation. Work equals force times distance. EPE equals mgh. So only a few of these are going to matter. So ke equals half mv squared, and power equals work done over time equals energy over time equals force times velocity. There's one more about efficiency, but we don't need that. So first, work done. How does this translate in rotational kinematic? So yeah, okay. So yeah, work is equal to what? So the force version is the force version in rotational kinematics. So yeah, yeah, you saw the equation just now. So work is equal to torque times the angular displacement. Yeah, yeah. So and you can find it redirects back to FD. And EPE, you clearly don't need it. Then what about KE? How does KE translate in rotational kinematics? So the KE, so the half remains as half, clearly. because the half remains as half, m becomes the moment of inertia and v becomes omega. And you can see if you expand moment of inertia, you can see it actually translates back to your half mv square. And this we don't really need it. We'll just use this. We use this. Wait. Okay, let me add this. So power equals torque. Force converts to torque. The V translates to omega. And if you expand torque again, yeah, you get back your V. So let me add these first. So here I've added the thing, and here is the chart for rotational linear parallels. Okay, so I leave you all. So yeah, so here's the chart, and that's all for this video, and bye bye. Yeah, that's all for rotational kinematics, and bye bye.